Okay, guys, we're going to do something that's very different for you guys, something you've never done before. Okay, down it. Mason, oh my God, Mason is talking. I'm trying to teach and Mason is talking. Oh, you're so bad. Okay, let me tell you, up till now, every concept, every term, every measurable quantity we've dealt with in this class had an object associated with it, right? Mass, an object has mass. Velocity, an object has velocity. Acceleration, object. Force, what one object does to another object. Okay, even energy, potential energy. I've got a mass a certain distance above the ground. That mass has potential energy. Spring potential energy, it is associated with the spring. But now today, you're going to learn about a quantity, electric field, which is a characteristic of a point in space. There's no object. Nothing has an electric field. An electric field is just a characteristic of a point in space. So that's the first thing you need to know. Electric field is a characteristic of a point in space. Let me tell you what else electric field is. And electric field is like, I don't know, those of you who read the Bible, I don't think kids read the Bible anymore, but you know how Jesus was always talking about the kingdom of God is like this. It's like a pearl of great price. Or the kingdom of God is like a man who sowed different types of fields. Well, electric field is like this. Imagine you go to Trader Joe's and you want to buy apples. And you know Trader Joe's sells apples by the apple. They don't sell apples by the pound, right? So you go gather 5 apples up and you take it to the man working there and you go, "Hi, how much do these 5 apples cost?" And he says, "Why, they cost $1.25. "Thank you." So you go back and you decide, maybe I want 7 apples. So you gather up 7 apples and you go to the Trader Joe's guy and you go, "Hi, how much do these 7 apples cost?" And he goes, "Well, $1.75. "Thank you." And then you go back and then you decide to get 10 and you get 10 apples and you go to the Trader Joe's guy and you go, "Hi, how much do these 10 apples cost?" At this point, what's the Trader Joe's guy going to say?
"Don't you get it? It's 25 cents an apple."
Thank you. It's 25 cents an apple, sir. Just count the number of apples you buy and you're going to multiply by 25 and that's how much it costs. Don't bother me anymore, right? Well, that's what electric field is like. Electric field says if there's a point in space and there's some charge over here, okay, and you want to see how much force this charge is exerting on your charge, you don't want to put 1 microcoulomb of charge there and then do Coulomb's law and calculate the force, and then remove that charge and put 2 microcoulombs there, do Coulomb's law and calculate that force, and then remove that and put 20 microcoulombs of charge there, and then do Coulomb's law and recalculate. You don't want to have to recalculate it every time. You want to have one number that tells you for every coulomb of charge that resides at that point, it's going to feel this amount of force. And that's it. Just multiply the number of coulombs by the electric field, and that's how much force you're feeling. Don't go to the Trader Joe's guy anymore. You see? And so that's what electric field is. So, hey, let me give you an example of this. Here, suppose I've got some repository of charge. Here, I've got a bunch of positive charge here. Because of the existence of that positive charge there, every point in space in the vicinity of that charge is going to be a location such that if some other charge resided there, it would feel a force. What?
Gavin needs to film the board. There you go.
I was paying attention.
That's okay. Gavin, we have our substitute videotaper today, Gavin Gaines. So I've got some point A in space, and because of the existence of this charge, any charge I put there is going to feel a force. The question is, how much force? Well, let's say I told you that the electric field equals 10 newtons per coulomb. Let's say I told you that's the electric field, and that's kind of weird that I did that. I don't know why I did that. 10 newtons per coulomb. That's the electric field. Then you tell me, oh, I shouldn't have put 10. I should have put 25 in keeping with my Trader Joe's story. Oh, that was dumb. Here, Trader Joe's story, 25 newtons per coulomb. So tell me, if I had 7 coulombs of charge here, how much force would it feel? Just like the apples, 175, right? What if I had 5 coulombs of charge here? How much force would it feel if every coulomb of charge is going to feel 25 newtons of force? What if I put 5 coulombs of charge here? How much would it feel? Yeah, 125 newtons. You see what I mean? What if I put 1 microcoulomb of charge there? Then how much force would it feel? 25 micronewtons, right? Because all it is 25 newtons per coulomb. If you've only got a microcoulomb, a millionth of a coulomb, you're only going to feel a millionth of 25 newtons of force, 25 micronewtons. You see? Just a second, I'm getting a telemarketer calling me. So the point is, if someone tells you how many newtons each coulomb of charge would feel at a certain point, then you don't have to keep recalculating Coulomb's law. You can just multiply by 25, like the Trader Joe's scenario. Is that okay with you guys? Okay, then I need to now define electric field with words. With words. Electric field. Okay? First of all, there's different ways to write electric field. Some people write it like this, electric field. And you'll notice the E has a little vector symbol over it because electric field is a vector. Or sometimes they just write it like this, just with the letter E with a vector, and everyone understands that to mean electric field. And the definition of electric field is, it's a characteristic of a point in space. A characteristic of a point in space it tells you how much force each unit charge would feel if it resided at that point in space. It tells how much force, and I'll say each coulomb, how much force each coulomb of charge would feel if it resided at that point. It tells how much force each coulomb of charge would feel if it resided at that point. There's another thing important about electric field. It tells you the direction, it gives you direction, and specifically the direction of the electric field is the direction of force a positive charge would feel if it resided in that spot. Okay? The direction of the electric field is the direction of force a positive charge would feel. If it resided at that point. So for example, in this scenario where I've got some repository of positive charge here, and I've got this point in space A that I'm interested in, what's the direction of the electric field at point A? Is it to the left or to the right? Well, what you do is you say, okay, what if a small positive charge resided there? And I call that a test charge, and I'll talk about that later on when we get to part C, where we get the electric field near a point charge. But I just pretend I have some small positive charge there. I make it small because I don't want it to be influencing everything around it. So it's a small, teeny positive test charge. What's the direction of force that this charge would feel, left or right? Right, it would be repelled, correct? And so the electric field would point to the right. So that's the direction of the electric field. Hey, let's do some problems. You guys ready? Good. I saw Brianna nod her head, and that's good enough for me. Example number 1, okay? I've got some big repository of negative charge. And I want to know what the electric field is at this point A. Well, just like the Trader Joe's scenario, what the most convenient way to discover the electric field at a point would be to grab a bunch of charge and go to the worker and ask, how much does this charge cost? You see? But what I'm going to do is I'm going to put some charge there, and I'm going to find out how much force that charge is feeling, and then you can find the electric field. So here we go. Suppose, let's say 20 microcoulombs of charge resides there. And suppose that 20 microcoulomb of charge feels 0.005 newtons of force. Could you get me the electric field? The electric field which tells me force per unit charge? Well, someone tell me, how are you doing this? Yes?
So you take the 0.05 newtons and then you divide it by the microcoulombs, but you're going to have to convert it first, and then you get 10 to the negative 7.
Thank you. You guys okay with this? This idea that if I want force per unit charge, I'm going to have to know what the force is, and I'm going to have to know how much charge is residing at that point, force over charge. And so ordinarily we write this formula just E equals F over Q. And that's the first most basic formula about electric field. It's just force over charge, force per unit charge. So yeah, you guys know to do that, you're going to put 0.005 newtons divided by 20 times 10 to the negative 6 coulombs. And we are going to have the units being in newtons per coulomb, not newtons per microcoulomb, even though arguably newtons per microcoulomb might be more, convenient. But the fact is, MKS units is coulombs, not microcoulombs, so we're going to go with coulombs. And what'd you guys get for that? Anyone do that division? Or am I going to have to do it? What'd you get? 250? Beautiful. You guys okay? 250 newtons per coulomb. Okay? Now, there's one more thing I would want, and that's the direction of the electric field. You tell me, in which direction is the electric field at point A? Who wants to tell me? What direction? Oh, please. Yes, Noel, tell us. How'd you know it's to the left?
Because you have the negative charges over there, and that's like all those charges, so it's going to attract.
Thank you. Because whenever we want the direction of the electric field at a point, we picture a positive test charge residing there. And that positive test charge would feel a force to the left. So the electric field is pointing to the left. So you'd say 250 newtons per coulomb to the left. Okay? Okay. Can I give you another type of problem? Okay, thank you. Here it goes. By the way, this was example number 1. Okay, oh, there it is. I put it there. Never mind. Here comes example number 2. Okay. The electric field at point A is 5,000 newtons per coulomb. A negative charge at point A feels, let's say, 2.0 newtons of force.
That's cool.
Is that kid walking by?
Yeah.
Did he do that?
He just rubbed his
That is so loud. You just do it. I mean, he didn't even need like a stick or something, just his fingers.
When she got up and sprinted out the door.
Who's this?
So sophomore year during sixth period, some kid did that and like ran their fingers around the A building, and Miss Min got mad, and she jumped up out of her seat and sprinted out the door to go yell at him.
Nice. Wow. That's a side of her I've never seen. Good for her.
I've seen this movie for neighbor.
Kick butt, man. Okay, what am I saying here? Okay.
Huh?
A,
I don't know if one of them. I don't
Find-
know if this.
find the, find the charge, and then B, feels 2 newtons of force to the left. I'm so sorry, I'm making this up as I go. So you guys okay, E field at point A is 5,000 newtons per coulomb. A negative charge at point A feels 2.0 newtons of force to the left. Number 1, find the charge, and part B, find the direction of the electric field. Okay, good luck. I'll give you a hint. For part A, use that formula. Yes? Sure. We'll say it on video. Justin Hamill has to go to the bathroom right now.
Can you be saying
You guys done?
Wait a minute.
Everybody done? Okay. Find the charge. Are you using E equals F over Q? So my electric field is 5,000 newtons per coulomb. My force is 2.0 newtons, and I'm going to find my charge. So my charge is equal to 2 over 5,000. And by the way, that's 2 newtons over 5,000 newtons per coulomb, which simplifies the coulomb. What'd you guys get? What's 2 over 5,000?
4 times 10 to the negative 4.
4 times 10 to the negative 4? Okay, good. 4 times 10 to the negative 4 coulombs. How many people got 4 times 10 to the negative 4 coulombs? Yay. How many microcoulombs would that be?
1 over.
You know, microcoulombs is times 10 to the negative 6. So if I'm going to increase, decrease that exponent by 2, yeah, 400. Absolutely. So that's going to be 400 microcoulombs. So be careful on an AP exam, if this were multiple choice, your choices would probably be like 400 microcoulombs. Okay, and tell me, what's the direction of the electric field if that negative charge is feeling 2 newtons of force to the left? What's the direction of the electric field? You guys okay with that? I've got a negative charge that's feeling a force to the left. So what's the direction of the electric field? How many people are thinking to the right? Okay, 5 of you. I wish it was like 25 of you.
Woo!
Someone tell me, why is the electric field to the right? Why isn't the electric field to the left, the direction of force? Yes?
So,
Fatima.
when you find the electric field in the beginning, you're using a positive charge.
Yes.
So, since you replace that with the negative charge, and the negative charge feels the force to the left, that means it's being attracted, and that means that there's already a positive charge.
Okay, so you were kind of picturing what was causing the electric field. And you're going, hey, if I've got some big repository of positive charge here forcing this guy to the left, then the electric field, the force of positive charge would feel if it resided there, would be to the right. And that's fine. Yeah, however you want to think of it is fine with me. Just so long as you know that the electric field tells you the direction of force a positive charge would feel. Which means if it's a negative charge feeling a force to the left, the electric field must be to the right. Okay. Any questions or problems on this so far? Okay, then let's go further. We're now going to talk about the electric field in the vicinity of a point charge. How do you spell vicinity? Vicinity? Vicinity.
I don't think there's a
Vicinity?
Vicinity.
Yeah, vicinity.
Oh, vicinity.
Yeah.
Vicinity.
no.
Vicinity.
Actually, there may be an S.
There is not.
I think there is an S.
So much.
That looks
I'm gonna
right.
look it up.
Mr. Shea.
Thank you very much. We're good. We're good, man. E field in the vicinity of a point charge.
Dude, you know I see.
Okay. So, how do you spell? Is that correct for vicinity? Oh, that's serious. How do you spell vicinity?
There's no S.
No S in that word.
Yeah, there's no S.
No S?
Just trying to spell with an N the first time.
Well, hey, Monty, I still think we're correct. It should have an S. Vicinity.
In the UK.
O-U-R. Okay, great. Well, a E field in the vicinity of a point charge. So let's say I've got some point charge here, some point charge there. Because of the existence of this point charge, every point around it is going to have an electric field associated with it. Because any charge I put nearby is going to feel a force due to that guy, right? And so now I'm going to say, okay, let me get a general formula for the electric field due to the presence of this guy. That is the electric field nearby due to his presence. Let's choose some point here, point A. And I'm going to say point A is some distance r away. And just like I did here, the Trader Joe's thing, if I want to know the electric field at a point, the most convenient way is to put a charge there and ask how much force it feels. And once I know how much charge is there and how much force it feels, I can get force per unit charge, and that's the electric field. Well, that's what I'm going to do here, but the charge I'm going to put here is my small positive test charge, Q naught. And at this point, I do want to define Q naught, okay? Small positive test charge. And that's a physics thing. Every physics book, if they have a small positive test charge, they always call it Q naught, and you always think about that. Okay? So I'm going to get the equation just like I did that problem there. Electric field is going to be force over charge. The force that this charge feels divided by what this charge actually is. I hope you see, tell me, what formula am I going to use for the force that that charge feels? Thank you very much, Fatima. I'm going to use Coulomb's law, right? That gets me the force between two charges a certain distance r apart. So that force is going to be K times Q times the test charge over r squared. And then I'm going to divide by the amount of charge residing there, which is Q naught. So tell me, why am I able to use Q naught even though I don't know what it is particularly? Yeah, it cancels out anyway. And I end up with my happy little formula, which is KQ over r squared. And that's going to be the electric field in the vicinity of a point charge, KQ over r squared, where Q equals the charge responsible for the electric field. Okay, he's responsible for it. His presence creates an electric field everywhere around him. And then of course R is equal to the distance from Q. So you guys ready to do a problem? Okay. Here comes example number whatever. Okay, or how about this? Point A is 0.3 meters to the left of a 20 microcoulomb charge. Point A is 0.3 meters to the left of a positive 20 microcoulomb charge. Find the electric field, both magnitude and direction. At point A. Good luck. Hopefully you're mindlessly plugging into that formula.
You bet.
9 times 10 to the 9th. Coulomb's constant, 9 times 10 to the 9th. You can remember it because like it's 9, and then like the exponent is also 9. I actually round, it's 8.99 times 10 to the 9th. We're going for 39. It's better. Alrighty, electric field equals K Q over R squared. So I got 9 times 10 to the 9th times 20 times 10 to the negative 6 over 0.3 squared. So that's 0.09, that's 2, that's 11, that's 5, that's 20. Are you guys getting 200,000? Is it 200,000?
2 million.
2 million.
2 million? I blame Chris. I blame Chris.
Oh, you just.
Yeah, 2 million. Because that's 20, that's not 2. I don't know what I was thinking. How many people got 2 million newtons per coulomb? Yay. Okay, good for you guys. Okay, 2 times 10 to the 6th newtons per coulomb. Okay, great. Here's my next question. Point A, here's point A, is 0.3 meters to the left of my 20 microcoulomb charge. So tell me, what's the direction of the electric field? How many people are saying it's to the left? How many people are saying it's to the right? Wait, so I only got like 6 or 7 people voting. Remember, the electric field is at a point in space is the direction of force a positive charge would feel if it was residing at that point in space. So this guy's positive 20. I've got a positive little test charge here. What's the direction of the electric field?
To the left.
How many people say to the left? Yeah, good for you guys. Absolutely. The electric field is to the left. Okay, great. Hey, let me give you one more type of problem. Here we go. Here, I've got a positive 2 microcoulomb charge here, and I've got a negative 3 microcoulomb, or how about if I make it negative 5? Yeah, let's make it negative 5. I've got a negative 5 microcoulomb charge here, and I've got a point right there, point A, which is 3 meters away from this guy and 1 meter away from that guy. Okay? Point A is under the influence of 2 separate and distinct charges, right? This guy and that guy. He's in the vicinity of 2 charges. I want the electric field at A. Someone tell me, how am I gonna get the electric field at A? What's my strategy? Yes, Fatima?
Find the electric field between both of the, A and both of the spheres. Yeah, and then add that.
Okay, first of all, is everybody okay that she's gonna treat them separately and then combine them? That, you see, she's gonna get the electric field as if only this guy was there, and then the electric field only if this guy was there. But then you've gotta decide, do you add or subtract them? Those two electric fields. And someone besides Fatima, tell me, do I add or subtract those two electric fields?
I was thinking subtract, but
Okay, we have one vote for subtract.
I vote
What
for
do you
add.
guys think, add or subtract? Yes, Noel?
Okay, so if you do the negative charge, like as a negative in the formula, then can't you just add the?
No, don't do the formula. Put them all in as positive. You've got to use your common sense. I love you dearly, Noel. Yeah,
I
don't do
have
that.
common sense.
Yes, you do. You do indeed. But yeah, don't be doing that. I want you to use your common sense. How are you commonsensically going to figure that out? Yes, Alejandro?
You add.
Don't you add them because they're acting in the same direction?
Thank you. You've got to decide what direction each individual electric field is acting in, and then if they're acting in the same direction, they add. If they act in opposite directions, they subtract. And don't depend on algebra or arithmetic. You've got to use your common sense. This charge here is exerting an electric field to the right, correct? Because if I put a positive test charge there, it would feel a force to the right. This guy is exerting an electric field to the right. You see it? So I'm going to add those two. So let's go ahead and do the problem. And I'm pretty confident you guys can plug into that formula. So let's just do it. Due to the 2 microcoulomb charge, the electric field is going to be K times 2 microcoulombs over 1 meter squared. Okay, that's 18 times 10 to the third, that's 18,000 newtons per coulomb. Okay, for the negative 5 microcoulomb charge, electric field is K times 5 microcoulombs over 3 meters squared. Okay, so the 9 cancels, leaving a 5. So it's just 5,000. And I want to say again, I do not want you putting positives and negatives in here. You're going to have to use your common sense to decide on the direction. So tell me, what's the electric field at point A? How many newtons per coulomb?
23,000.
Yeah, 23,000. You add them up. The electric field is going to be 23,000 newtons per coulomb. And which direction is it point? Yeah, to the right. Okay. Let me give you a chance to write this down, and then I'm going to give you one more problem, then we'll call it quits. Okay. You guys ready for the next oh, let me wait. Yay, Anna Easton's back. You ready for the next problem? Here it comes. Same scenario, same everything, only now this is negative 2 microcoulombs. I'd like everyone to please tell me, what's the electric field at point A now that this is negative 2 microcoulombs, not positive 2? If I were to call this 5,000 newtons per coulomb and I call that 18,000 newtons. Okay, you guys ready? There's your three choices. Which is it? I have just turned this negative. Tell me, how many people say it's 20, now it's 23,000 newtons per coulomb, but to the left instead of the right? Couldn't get anyone to bite on that. How many people say 13,000 newtons per coulomb, but it's to the left instead of the right? Okay. How many people say 13,000 newtons per coulomb to the right? Okay. Let me ask you, why is it to the left? Why not to the right? Go ahead, Imani.
It's the 18,000 newtons per coulomb is to the left.
Thank you. The big guy is to the left, right? The 18,000 Newton Coulomb guy is to the left. So now the resultant is going to be 13,000 to the left. And again, there's no other way to do it except to use your common sense. There's no way algebra would have gotten us there, arithmetic would have gotten us there. And I keep hammering that home because it's so important to getting electric field problems right, to never ever plug negatives into your formula and rely on your common sense. Okay, hey, that's it for electric field. Remember, electric field is force per unit charge. Remember, the direction is the direction of force, a positive charge in field. It's a characteristic of a point in space. And then you got your formula for an electric field near a point charge, EQ over R squared. Bye-bye.